So in this beautiful experiment that they did, they had people drag behind this tractor while they're walking along on the treadmill, and the treadmill biomechanical speed could either be faster or slower than the perceived speed driven by the tractor. And then when they got off the treadmill, they pulled down a blindfold and walked a distance that they were told to walk, and they either overshot or undershot based on the mismatch between the biomechanical speeds and the real speed. And so, thank you. We obviously didn't want to drag rats around on a tractor, so that's why we built the dome. As Yotaro mentioned, and sort of Jim, the rat walks these circular laps, and then we can move the forest, so to speak, move the landmarks as a function of the animal speed in a behavioral closed loop to get the perception that its biomechanical speed and its perceived speed are different, to create that experience for the animals. Just to provide a different way of looking at it than you've seen so far today, on the left, we're going to see, not very well, you won't be able to see the rat, but what you will see is individual blue dots that represent when a particular plate cell fired in the laboratory frame of reference during one of these game manipulations. So the landmarks are rotating, and if you look closely at the center, you'll see this hemispherical mirror. You can actually see the landmarks rotating on that hemispherical mirror to give you a sense of the fact that the animal's walking around and the plate cell is going to be firing kind of random locations. In this frame, we've digitally stabilized the landmark. So this is the landmark frame of reference. And in this video, you'll see the plate cell keeps firing in a consistent location. And so if you look on the left, the landmarks are rotating around, and the plate cell is firing multiple times per lap. But on the right, there's a little bit of a digital artifact in our stabilization. And now all at once we turn off the landmarks, and now the animal is just foraging around for its chocolate milk. And as it does, its plate cells are firing at approximately the same location in what would be this virtual frame of reference given by the landmark if we had still had the landmark show. So just another way of looking at that same data that Jim showed earlier. Again, x-axis is distance in the lab frame, y-axis is either in the landmark frame or the lab frame. And so each gray and white bar is a different lap in the laboratory frame. Different bar, in the virtual frame of reference. And then, so you can see both the virtual frame of reference by the gray and white bars and the lab frame of reference by the x-axis. And this particular plate cell likes to fire around 270 degrees in the landmark frame of reference. And the hippocampal gain, therefore, kept pace with this experimental manipulation. And it did not go back to a unity gain. It didn't go perfectly to the lab frame, the landmark frame. Instead, it went to this intermediate value, as you already saw. So, and there were multiple recorded plate cells in that session. And I actually think this is a really beautiful example of really pure path integration happening with multiple plate cells firing in sequence, all sharing the same gene. This is how I, as an engineer, became really convinced that path integration was a real thing. We've been looking at the data from Ravi and Manu, who are the lead authors on that stuff. And as Jim showed, every individual color here is an individual rat. Every dot is an individual session for that rat, and for different experimental gains, we got different recalibration effects. And I was asked last session, why don't we get a gain perfect recalibration? Also known in like the visual motor rotation path, there's often a residual error that's never quite cleaned up by cerebellar learning and visual motor rotations, and the same thing may be going on here. I don't know how long we need to run the experiment to get to perfect recalibration. But that error, that discrepancy is going to come up later. So treat that as a kind of placeholder. So, so that was a quick review. Path integration is plastic and can be recalibrated. And there are several studies, including a recent paper that's in review on head direction cells, as well as it can be recalibrated by optic flow. I didn't talk about that data. The main information we've seen today is on recalibration by landmarks. But today I want to focus on the modeling of that at our postdoc work in Seeker. So this is Gorkem, and this is the paper that finally came out. I'm not going to possibly go into even a fraction of the detail in that paper. There's a 53-page appendix of solid mathematics. He spent hundreds of hours on that, dozens of hours at my chalkboard proving that he was correct. and it's really quite a tome of work. But I will try to pick up on some highlights of his modeling. So what he's done is he said, okay, we're not really thinking about a head direction system, but let's use a ring attractor anyway as a simplified model for our experimental setup. After all, the animal is walking around in circles. And so rather than going through the hassle of modeling, say, a sheet attractor, let's just model it as a ring attractor for simplicity. Or let's assume that the feed-forward model that Utaro has shown is disproven is at play. But for simplicity, we're just going to model this as a ring attractor. So what is this ring attractor idea? For those that aren't familiar with this field, the idea is that you have this central ring, and there's a bump of activity that emerges on that central ring due to a local excitation and global inhibition pattern of the connectivity of that ring. And so this bump emerges, and that bump represents the internal representation of the animal's position on this ring attractor network. And then what happens is when the animal begins to walk around in circles, something biases that bump and causes it to shift along the ring. And the way that works is that there are these velocity inputs coming into these side rings called rotation rings. And as the animal is going counterclockwise, this velocity neuron will begin firing more, and this one will begin firing less, creating a kind of push-pull. And because of this offset reciprocal connections, what happens is that as the animal is walking, say, counterclockwise, the blue ring bump gets higher, and the red bump gets lower, and the connections back to the central ring create a bias and cause the bump to start to shift around. All the while, if the landmarks are on, there's a correction that's coming down from a visual system that's adjusting that path integrator, making sure it doesn't stray too far off course. Okay, and so the very simple idea is that the bump velocity is governed by the physical velocity times its gain factor plus a landmark-based correction. And so if the thing is all tuned up, then you can purely path integrate and keep track of your position. If your path integration gain is poorly tuned, then you're going to be over or underestimating your motion, and the bump of activity will move too fast or too slow relative to your physical movement. Okay, and so the path integration gain, as Jim mentioned earlier, is typically hidden when the landmarks are on, but when the landmarks are off, it reveals itself because there's no global landmarks correcting it all the time. So we treat that as if that's the path integration gain. So this is a complicated model. Gorkin applied classical techniques that were known in the literature for taking that complicated model and reducing it down mathematically to a simplified form in a formal model reduction framework. And it basically ends up being that the velocity d theta by dt, that's the rate of change of the angular position with respect to time, has a landmark-based correction term plus this path integration term. And there's a couple of things that I want you to notice about this. First of all, the path integration term depends on the angular position of the animal, because after all, this is a distributed network. And so, in fact, this is the only big equation that I'll show in this talk. But I do want to show this because it's a really beautiful piece of analysis that he did, where he said, let's take the whole network and let's analyze it using this reduction technique to see what are the factors in this network that contribute to the gain that most people have sort of swept under the carpet. And what he found is that there's obviously the gain of the velocity neuron, plus the synaptic connections from the velocity neuron to the rotation ring, plus the synaptic connection from the rotation ring to the central ring, and some details about the bump geometry and bump time constants, all can contribute to this. And he painstakingly and meticulously analyzed each one of these possibilities in the paper. But the basic idea is that positional feedback from landmarks directly corrects the path integrator through an implicit process that's been known for many years, and then indirectly creates a source of error between the landmarks and the path integrator that creates a representation of that error in the network, and then through a plasticity process updates this.
That's the basic idea of the model. The model makes three
predictions that I'm going to go through quickly. One is that place fields should drift, and I'll go over why and what that means. Second, the network, he proved under certain circumstances, the network must have an explicit representation of error, not just the fact that the visual bump and the internal representation are different, and that's an implicit error, that somehow a neuron must fire more or less as a function of the distance between those two bumps as an explicit error code. And then finally, he was able to use this model to predict the extent of recalibration based on the drift and the error code. And so what is the drift? It's actually a prediction in hindsight. We actually knew about this drift in Ravi and Manu's original paper. And the idea is very simple. So if the gain is greater than 1, that means that I'm going to get to the landmarks before I think I should have if I haven't recalibrated. And I don't think I should be there yet, then maybe a particular place cell might be active yet. And there'll be a fusion, like a Bayesian combination of my path integration to that landmark. And I'm going to fire a bit late. You can see that here in this example trace. And the converse is also true. If I make a gain less than 1, then I'm going to get to the to where I think the landmark ought to be, but it's not going to be there yet because the landmark's moving along with me at a slightly slower speed. So I'm going to see the landmark now. And I'm not seeing the landmark, and the neuron will fire a bit early before it gets corrected by the landmarks. And so that turned out to be true in hindsight. The next two predictions we didn't know to look for. This is an example where the model has caused Workman to go back to our original data and find things in it that we never noticed. And the basic idea is that as this drift is occurring, he also predicted that we ought to see higher firing rates in some neurons and lower firing rates in others. He had no, depending on where the cytoplasticity was, it could be in either direction. That's a technical detail. And quite beautifully, that firing rate should be correlated with the drift, which is a measure of the error between the path integrator and the visual landmarks. And he found quite beautifully that across his individual sessions and across sessions, we see this really nice relationship between the drift and the firing rate of the neurons. That was not something we need to look for. And so that was one neuron. If you look at a lot of neurons, and then just look at the ones with very strong correlations between drift and firing rate, and choose those as candidate error encoders, and focus our attention on these candidate error encoders. Well, let me just say that there's a large number of them, far more than chance, 45% of them. And let's take those now and see if we can predict the extent of recalibration based on those error encoders. And so remember this residual error and the recalibration. So notice that the firing rate goes up, and then it starts to come back down. Why is the error going down? Because the system's recalibrated. It's no longer developing and sustaining this error between path integration and landmarks because the system's recalibrating. And so there's this final path integration gain that we measure after we turn off the landmarks, and there's this residual, and then there's the firing rate that goes up and then comes back down. He uses this residual firing rate relative to the initial baseline to predict the degree of recalibration. And he finds that when he uses the candidate error encoding neurons, he gets a beautiful prediction of the extent of that recalibration. And when he looks at the other neurons, it does not. Just the last little tiny piece, this is the last slide, is that the error encoding neurons happen to be near landmarks, which makes a lot of sense because when you're far away from the landmarks, you don't know exactly how much error you've accumulated. And so, put my acknowledgement slides, the rest is just the thing. So these are the amazing people that worked on it. And we have another CRCNS. Okay. That's it.
There's a couple minutes for questions.
One of you here? You can go first in the front there. Yep. Well, we are starting to notice that there are idiosyncratic properties of the individual cells, as well as the number of neurons that we're finding near the landmark versus neurons in space. We don't have a full picture of that, but I think we're starting to move away from this idea that there's just this gestalt visual world, and that all landmarks are equal and the animal position is based on just a global panorama, and that there really is a strong local influence of landmarks as well. Oh yeah, go see Barat's poster later Yep. So that's a very good question. These experiments are 45 minutes because we slowly boil the frog. We slowly boil the frog. That's mine.